A dream written in starlight. Look up on a dark, clear night. If you know where to look, you might see a faint smudge of light in the sky. That's the Andromeda Galaxy, the closest major galaxy to our own Milky Way. It contains about 1 trillion stars, countless planets, and mysteries we can barely imagine. For centuries, humans have dreamed of traveling to distant worlds. We've landed on the moon. We've sent robots to Mars. We've launched spacecraft beyond the edge of our solar system. But Andromeda? That's a different challenge entirely. It's so far away that even thinking about the distance feels impossible. Yet the question remains, could we ever reach it? And if we tried, how long would it take? The answer is both heartbreaking and beautiful. The distance, an ocean of empty space. Andromeda sits roughly 2.5 million light-years from Earth. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. Light moves at 300,000 kilometers per second, the universal speed limit. Nothing in the universe can move faster. So even if you could somehow travel at the speed of light, it would still take you 2.5 million years to reach Andromeda. To put that in perspective, when the light we see from Andromeda left that galaxy, humans didn't exist yet. Our ancestors were still evolving in Africa. Entire ice ages have come and gone since that light began its journey. And we're not even close to traveling at light speed. Our fastest spacecraft, a cosmic crawl. The fastest human-made object ever launched is NASA's Parker Solar Probe, which reached speeds of around 700,000 kilometers per hour as it dove near the Sun. That sounds fast. But compared to the speed of light, it's a snail's pace. At that speed, it would take the Parker Solar Probe roughly 4 billion years to reach Andromeda, longer than the current age of planet Earth. Even Voyager 1, which has left our solar system and is now drifting through interstellar space, would take over 50 billion years to cover that distance. By that time, the Sun itself would have died. Advanced engines, cutting billions to millions. Let's imagine we built much faster ships. Not just rockets, but advanced propulsion systems using ideas from cutting-edge physics. Fusion engines. These would burn hydrogen like the Sun does, releasing enormous energy. They could theoretically push a spacecraft to maybe 10% the speed of light. At that speed, the journey to Andromeda would take 25 million years. Still impossibly long. Antimatter engines. Antimatter is the most energy-dense fuel imaginable. When matter meets antimatter, they annihilate completely, turning into pure energy. If we could harness that, we might reach 50% the speed of light or more. That cuts the trip down to around 5 million years. Better, but still far beyond a human lifetime. Or 1,000 lifetimes. Time dilation, a strange gift from Einstein. Here's where things get weird. According to Einstein's theory of relativity, when you travel close to the speed of light, time slows down for you compared to everyone else. If you were aboard a near-light-speed ship traveling to Andromeda, you might experience the trip in just a few decades or centuries, depending on how fast you're going. But back on Earth, millions of years would pass. Your friends, your family, your entire civilization would be long gone. The continents would shift. Species would evolve and go extinct. Humanity itself might vanish. You'd arrive at Andromeda as a ghost from a forgotten age. Wormholes and warp drives, bending the rules. So what if we didn't travel through space, but bent space itself? Wormholes. These are theoretical tunnels through spacetime. Imagine folding a piece of paper so two distant points touch, that's the idea. If wormholes exist and can be stabilized, they might let us cross vast distances instantly. But we've never seen one. We don't know if they're real. And even if they are, creating or controlling one might require technology far beyond anything we can imagine. Warp drives. Inspired by science fiction, a warp drive would compress space in front of a ship and expand it behind, letting the ship surf through space faster than light, without actually moving faster than light locally. It's allowed by Einstein's equations. But it requires exotic matter with negative energy, something we've never found and might not exist. Right now, warp drives are beautiful math. Not machines. The cosmic twist, Andromeda is coming to us. Here's the most amazing part of the story. We may never fly to Andromeda, but Andromeda is flying to us. The Andromeda Galaxy is moving toward the Milky Way at about 110 kilometers per second. In roughly 4 billion years, the two galaxies will collide. Don't worry, collide doesn't mean stars crashing into each other. Space is so vast that stars will mostly pass by like fireflies in the night. But the galaxies will merge. They'll dance around each other, their spiral arms tangling, their stars mixing. Eventually, they'll form a single, giant elliptical galaxy. Some scientists call it Milkomeda. And Earth? If it still exists, it will be part of this new cosmic world, with a sky full of stars from two galaxies. Conclusion: a journey humanity may never take. So, could humanity ever reach Andromeda? With current technology? No. With advanced engines? Theoretically yes, but it would take millions of years. With exotic physics like wormholes or warp drives? Maybe, but we don't know if they're even possible. For now, Andromeda remains a dream written in starlight. A reminder of how vast, strange, and beautiful the universe truly is. But we don't need to reach it. Because in the grand story of the cosmos, Andromeda is coming to us. And when it does, the universe will create something entirely new. A cosmic dance 4 billion years in the making. Imagine standing on Earth 4 billion years from now. You look up at the night sky, and it's unrecognizable. Where once there was a faint smudge called Andromeda, now there's a blazing river of stars stretching across half the sky. Brilliant blue giants, glowing red supergiants, and swirling clouds of gas fill the darkness. The Milky Way and Andromeda are no longer separate. They're locked in a gravitational embrace, spinning around each other like cosmic dancers. This isn't science fiction. This is the future, written in the laws of physics. The collision has already begun. Andromeda is racing toward us right now, and nothing can stop it. So what happens when two galaxies collide? Will Earth survive? Will the Sun? And what will this new galaxy look like? Let's step into the future and watch the greatest cosmic event our corner of the universe will ever see. The approach, a sky transforming. Right now, Andromeda is just a faint blur in our night sky. You need dark skies and sharp eyes, or a telescope, to see it. But as millions of years pass, it will grow. In 2 billion years, Andromeda will appear larger than the full moon. It will dominate the night sky, a glowing spiral of light visible even in cities. In 3 billion years, it will stretch across the heavens like a shimmering bridge. Star clusters and nebulae will be visible to the naked eye. And then, in 4 billion years, the collision begins. But here's the strange part, even though two galaxies are smashing together, stars almost never hit each other. Why? Because space is empty. The first pass, stars like fireflies. Galaxies look solid in pictures, packed with stars. But the truth is, they're mostly empty space. Imagine shrinking the sun down to the size of a grain of sand. On that scale, the nearest star would be 8 kilometers away. So when Andromeda and the Milky Way pass through each other, their stars don't collide. They pass by like fireflies in the night, never touching. But even though the stars don't crash, gravity changes everything. The two galaxies tug on each other. Stars get pulled from their orbits. Some are flung out into deep space. Others spiral inward toward the galactic centers. Long, graceful tidal tails, streams of stars and gas, are pulled from both galaxies, stretching millions of light-years into the void. From a distance, it would look like two jellyfish tangling in slow motion. The dance, orbits of chaos. After the first pass, the galaxies don't merge immediately. They swing around each other like a pair of figure skaters. Each orbit brings them closer. Each pass rearranges their stars. The beautiful spiral arms of both galaxies, delicate structures shaped by billions of years of rotation, begin to break apart. Stars that once orbited in neat, orderly paths now move in wild, chaotic directions. The night sky, if you were watching from a planet during this time, would be a constantly shifting masterpiece. New constellations would form every million years. The sky would be brighter than anything we see today, filled with young blue stars born from colliding gas clouds. The starburst, a firestorm of creation. Here's where things get dramatic. While stars rarely collide, gas clouds do. Both galaxies contain enormous clouds of hydrogen gas, the raw material for making stars. When these clouds crash into each other, they compress. And when gas compresses, it heats up. And when it heats up enough, new stars ignite. This is called a starburst event, a sudden, explosive wave of star formation. For a few 100 million years, stars will be born at an incredible rate. Thousands, maybe millions of new stars will light up across the merging galaxies. Massive blue giants will blaze for a few million years, then explode as supernovae, scattering heavy elements like carbon, oxygen, and iron into space. These elements will seed future planets. Future life. The collision that destroys two galaxies also creates the building blocks for new worlds. What happens to Earth? Now the question everyone wants answered: will Earth survive? The short answer: probably. Even though the galaxies are colliding, the chance of our Sun directly colliding with another star is incredibly small, less than 1 in a trillion. But Earth won't escape unscathed. The Sun's orbit around the galactic center will change. We might be flung outward, into the quiet suburbs of the new galaxy. Or we might spiral inward, closer to the chaotic core. If we're unlucky, we could be ejected entirely, cast out into the vast emptiness between galaxies, where the night sky would be almost completely black. But there's a bigger problem. The Sun's final days. Even if Earth survives the galactic collision, the Sun won't. In about 5 billion years, around the same time the galaxies finish merging, the Sun will run out of hydrogen fuel in its core. It will swell into a red giant, expanding so large it might swallow Mercury, Venus, and possibly Earth. Even if Earth isn't consumed, the oceans will boil away. The atmosphere will be stripped off. The surface will become a lifeless, molten hellscape. So by the time the Milky Way and Andromeda finish their merger, Earth, if it still exists, will be a scorched, dead rock orbiting a dying star. Humanity, if we still exist, will have long since left. The birth of Milkomeda. After billions of years of chaos, the dance finally ends. The two galaxies settle into a single, massive structure. The graceful spirals of the Milky Way and Andromeda are gone. In their place is a giant elliptical galaxy, a smooth, football-shaped cloud of stars. Scientists call it Milkomeda. It will contain over 1 trillion stars. It will be one of the largest galaxies in the local universe. And somewhere inside it, if the Sun still shines, will be the remnants of our solar system, a tiny speck in an ocean of ancient light. The new sky, a galaxy reborn. If intelligent life still exists during this time, whether it's humanity or something else, they'll witness a sky unlike anything we can imagine. Instead of a faint band of stars, our current Milky Way, the night sky will be filled with a dense, glowing sphere of light. Stars will be packed closer together. The sky will be brighter. But it will also be lonelier. The other galaxies in our local group, small galaxies that orbit the Milky Way and Andromeda, will either be absorbed or flung away. And beyond that? Darkness. Because of the expansion of the universe, distant galaxies are moving away from us. In trillions of years, they'll disappear beyond the cosmic horizon. Future civilizations in Milkomeda will look out and see, almost nothing. They might think they're alone in the universe. Conclusion: a story of destruction and rebirth. The collision of the Milky Way and Andromeda is a story of endings and beginnings. Two ancient galaxies, shaped by billions of years of history, will be torn apart. But from their chaos, something new will be born. New stars. New worlds. New possibilities. It's a reminder that the universe is always changing. Nothing lasts forever, not galaxies, not stars, not even planets. But change doesn't mean destruction. It means transformation. And in 4 billion years, when Andromeda finally arrives, the universe will create something beautiful. Not because we flew there, but because the cosmos itself brought us together. When Titans meet. The story of the Milky Way and Andromeda merger isn't just about stars and gas clouds. Hidden at the heart of each galaxy lies something far more dramatic. A supermassive black hole. The Milky Way's black hole, called Sagittarius A*, pronounced A*, weighs about 4 million times the mass of our Sun. It sits at the center of our galaxy, quietly pulling stars into orbit around it. Andromeda's black hole is even bigger, roughly 100 million solar masses. A true cosmic giant. Right now, they're separated by 2.5 million light-years. But when the galaxies collide, these two monsters will be drawn toward each other. And when they finally meet, they'll perform the most violent dance in the universe. So what happens when supermassive black holes collide? Can anything escape? And what does this mean for the far, far future, not just of our galaxy, but of the entire universe? Let's dive into the depths of spacetime itself. The sinking, a journey to the center. When the Milky Way and Andromeda first collide, their black holes are still far apart, thousands of light-years away from each other. But gravity is patient. As the galaxies merge, stars and gas clouds swirl around the center. Every time a star passes near one of the black holes, it gives up a tiny bit of energy. This process, called dynamical friction, slowly drags the black holes inward. Think of it like stirring honey with a spoon. The spoon moves through the thick liquid, but the liquid also slows the spoon down. Over hundreds of millions of years, the two black holes spiral closer and closer. Eventually, they enter the final phase, the binary. The binary, locked in orbit. Once the two black holes get close enough, they lock into orbit around each other. They circle faster and faster, drawing closer with every pass. At this point, something incredible happens. They begin to emit gravitational waves, ripples in the fabric of spacetime itself. These waves carry energy away from the system, causing the black holes to spiral inward even faster. It's like a cosmic whirlpool, pulling them together. As they get closer, the gravitational waves become stronger. The black holes orbit faster. And faster. In the final moments before they merge, they're spinning around each other hundreds of times per second, releasing more energy than all the stars in the visible universe combined. But this energy isn't light. It's spacetime itself, shaking. The merger, a silent explosion. And then, they collide. Two supermassive black holes, each containing the mass of millions or even billions of suns, slam together. The event is unimaginably violent. The fabric of spacetime warps, twists, and rings like a struck bell. A massive burst of gravitational waves radiates outward, traveling at the speed of light across the universe. But here's the strange part, you wouldn't see anything. Black holes don't emit light. The merger happens in total darkness. No flash. No explosion. Just a ripple in the invisible structure of reality. What emerges is a single, larger black hole, weighing over 100 million solar masses, spinning rapidly and settling into a new equilibrium. Around it, the merged galaxy, Milkomeda, continues to orbit. Stars whirl in chaotic paths. Gas clouds fall inward, forming a glowing accretion disk around the new black hole. For a time, Milkomeda might become a quasar, one of the brightest objects in the universe, visible across billions of light-years. But eventually, the chaos settles. The black hole goes quiet. And the galaxy begins its long, slow journey into the future. Could humanity survive? The interstellar escape. Let's rewind for a moment and ask a human question: could we survive this? If humanity, or whatever we evolve into, still exists 4 billion years from now, we'll face a choice. Stay on Earth and die with the sun. Or leave. To survive the galactic merger and the death of our star, we'd need to become an interstellar civilization. Option 1, move to another star. We could build generation ships, massive vessels designed to travel for thousands of years, and migrate to younger, safer stars. These ships would carry entire ecosystems, plants, animals, frozen embryos, digital minds, cultural archives. The journey might take millennia. But time becomes less frightening when you're thinking across millions of years. Artificial habitats. We could abandon planets entirely and live in space habitats, rotating cylinders or spheres that generate artificial gravity. These habitats could orbit any star, or even drift freely through interstellar space, powered by fusion reactors or energy collected from stars. Entire civilizations could exist without ever needing a planet again. Option 3, digital transcendence. Perhaps by then, humanity will have uploaded its consciousness into machines. Digital beings don't need air, water, or warmth. They could exist on cold, distant worlds, or even drift through space in self-repairing spacecraft, thinking vast thoughts over millions of years. Time would mean something different to them. They could sleep through the ages and wake only when something interesting happens. The lonely future, when galaxies disappear. But let's keep going. Let's look even further into the future. Billions of years after the Milky Way and Andromeda merge, the universe itself will change. Right now, the universe is expanding. Distant galaxies are moving away from us, and that expansion is accelerating, driven by something called dark energy. In about 100 billion years, most galaxies outside our local group will be so far away that their light can no longer reach us. They'll vanish beyond the cosmic horizon. If a civilization exists in Milkomeda at that time, they'll look out into the universe and see, almost nothing. Just their own galaxy, surrounded by endless darkness. They might think they're alone. They might believe the universe consists only of their galaxy and nothing else. The evidence of the Big Bang, of cosmic expansion, of other galaxies, all of it will be gone, lost beyond the edge of observable space. The heat death, the universe grows cold. And then, trillions of years later, the final chapter begins. Stars will stop forming. One by one, the last stars will burn out. Red dwarfs, the smallest, longest-lived stars, will shine for trillions of years. But even they will eventually die. The universe will enter an age of darkness. Black holes will be the last surviving objects, slowly evaporating through a process called Hawking radiation, a quantum effect that causes them to lose mass over unimaginable spans of time. Even supermassive black holes, like the one at the center of Milkomeda, will eventually evaporate. The process will take 10 to the power of 100 years, a number so large it's almost meaningless. When the last black hole finally evaporates, the universe will be left with nothing but scattered particles, drifting through infinite space at near absolute zero. This is called the heat death, the final, quiet end of everything. No stars. No planets. No galaxies. No light. Just cold, empty space, expanding forever. A glimmer of hope, the unknown future. But here's the thing. We don't actually know if this is how it ends. Physics breaks down when we try to predict things trillions upon trillions of years into the future. There are mysteries we haven't solved. Forces we don't understand. Maybe dark energy will change. Maybe the universe will collapse back into a big crunch and reboot itself. Maybe quantum mechanics will allow new universes to bubble into existence from the void. Maybe intelligence, whether biological, digital, or something we can't imagine, will find a way to survive, to create, to endure. The universe is far stranger than we think. And the future is longer than we can imagine. Conclusion, a story that never ends. The collision of the Milky Way and Andromeda is just one chapter in a story that spans eternity. It's a story of destruction and creation. Of chaos and beauty. Of endings that are also beginnings. 4 billion years from now, two galaxies will merge, and a new one will be born. Billions of years after that, the stars will fade, and the universe will grow cold. But even in that darkness, there might be something we haven't imagined yet. Because the universe has always surprised us. And maybe, just maybe, the story doesn't end. Maybe it transforms. Just like the galaxies. Just like us.